So hi, I'm here to help you out with the next part of this electrochemical cell set of videos. And this next part has to do with, what I'm calling the molecular level view of what's happening in a cell. And to start off with, I've got, once again, two half cells here, and I put copper and copper 2 plus as the electrolyte at 1 molar concentration here on the left. And we've got a silver electrode, metallic silver and silver plus ion here on the right. Also the electrolyte being at 1 molar solution. And as before, we've got this voltmeter up here, and we're gonna connect the red lead to the to this half cell over here. Okay, and then we'll connect the black lead to that half cell over there. And well, let's just first maybe go through a little pre-calculation just to make sure that we, as I've sort of set it up, I've kind of implied that on the left we've been putting the anode where oxidation takes place, and on the right the cathode where reduction takes place. So the question is that really the case? And you might want to look up some E-naughts in your appendix to sort of to confirm that. So if you want to go ahead and try that. Okay, then here's what we got going on here. If you look up the half reaction for the copper, you already know that as a reduction, that E0 is 0.34, and as a reduction for the silver plus picking up an electron, that E0 is 0.80. 0.80 is bigger than 0.34. So we're going to say that the silver reduction wins out and causes the copper to be oxidized. So that's why I've written the copper half reaction as an oxidation half reaction there. Solid copper goes to copper 2 plus a couple electrons. Here at this electrode, Ag plus picks up an electron and becomes silver solid. And here I've written the net ionic equation here, which couples those. Here's just solid copper combines with 2 silver pluses to produce copper 2 plus and 2 solid silvers. Okay, and so by what would be the E cell that you would measure for this? Well, now once again I've set up my black lead over here, the red lead over here. What would E cell be? Well, it's supposed to be E0 of the reaction, as you would calculate from the appendix, minus this Nernst correction. But remember, the Nernst correction will be 0 because all of my electrolytes are at 1 molar, so I get to ignore that. Now, what's that going to be? Well, I think it's going to be the E0 for the half reaction that's the reduction. That would be that. So E0 would be 0.80 minus the E0 for the what's going to be oxidized, 0.34, and so I get 0.46 volts is what the E cell ought to read right up there. So the other little piece of this then is I want to kind of talk a little bit about what's happening at the molecular level. So we now believe that electrons are going to be moving away and up the wire here. I'll draw that this way because we know oxidation is going on at that half cell. What must be happening is therefore that here's a copper atom. That copper atom, which is neutral here, has an oxidation number of 0. Now becomes copper 2 plus. What happened to its electrons? Well, they just traveled up here and eventually go up that wire. Okay. So we kind of have an increase of copper ion, positive ion concentration here in that cell, and that's going to be important in a little bit. But let's talk about what's going on at the cathode here. Well, I've got electrons coming down here. There's sort of a surfeit, an extra amount of electrons here. And if a silver ion happens to be close by there, I could say, hey, I want you electron, and so it combines with an electron to produce another silver oxidation number 0, just a metallic silver there. So the picture we have at the molecular level is that as this circuit is completed, we have an increase in copper ions here, plus ions there, and you notice what's happening here is that we're not, we're losing ions in solution here. Now, that itself can't go on for very long. In fact, it hardly goes on at all, because it would quickly create an imbalance of charges here. So what will have to happen is that these excess charges will have to leave here. I guess I should say that when we started off our electrolyte solution, perhaps this was silver nitrate, so NO3. There had to have been, a balance between the amount of silver ion and nitrate ion, and same thing here, NO2 minus NO2 minus 2 nitrates for every copper. So you see the problem here is that as we oxidize here at the anode, we have too many copper ions for the number of nitrates. Sorry, this is NO3. And so on. So what's got to happen? Well, that's the really critical role that the salt bridge, or also called a porous separator, is for. As we build up too much positive ion here, this separator here is just a little gel, and it's soaked in sodium nitrate, and the sodium nitrate can move through there, and other things, ions, can move into it. So we build up too much copper ion here, 2 plus here, that can go into that porous separator. Now you might think it would travel all the way through, but it doesn't really have to, because once it gets in on this side, there's some sodiums on this side, and they're ready to come out into that solution. Okay, and that's a good thing, right? Because we said that as we're using up silver ions here, we don't have enough positive ion over here. So that takes care of that, right? The other thing, of course, that could happen is that as we build up too much positive ion over here, we could have some nitrates that move out into there to balance that charge. That would be a nitrate maybe on this side of the porous separator that moves in, and it could be replaced by, in this case, a nitrate ion that's over on this side. Why would that solution want to do that? Well, as we take away Ag plus from the solution, we have too much nitrate, and so it needs to move out of that solution. So that's, in fact, this is why you have to have a porous separator or a salt bridge in order to get any, basically to complete the circuit.